So we've come to the last problem that we're going to work as an example in chapter 4. This is the most complicated one. It's actually a heat exchanger problem. So the heat exchanger problem is the most complicated. Turns out to be somewhat of a lengthy problem. So these problems don't necessarily show up on exam 2 as a full workout problem or one of the multiple choice questions because they are so lengthy and the time is limited for the exam. But sometimes the heat exchanger problems do show up as one of the concept questions, and it asks you something simple about the heat exchanger. Also with the heat exchanger problems, you might see one on the final. Since there's plenty of time to work on problems during the final, you might see a heat exchanger problem on the final. So let's start off, let's read this problem and talk about how to solve it. So R134A is to be cooled by water in a condenser. So a condenser is just a heat exchanger. It's a specific type of heat exchanger where whatever is the hot substance, in this case the hot substance is R134A. The hot substance typically will come in as a superheated vapor, and it's called a condenser because at the exit of the heat exchanger, the hot substance, in this case R134A, changes from a superheated vapor down to a liquid. So basically it condenses it. So we have two substances here. R134A is the hot one, and then the cooling substance is the water. So R134A, it enters with a mass flow rate of 6 kilograms per minute at a pressure of 1 megapascal and a temperature of 70 Celsius, and exits at a temperature of 35 Celsius. So it cools down a total of 35 degrees. Water enters the condenser at 300 kilopascal and 15 Celsius and leaves at 25 Celsius. Neglecting any pressure drops, determine the mass flow rate of the cooling water and the rate of heat transfer from the refrigerant to the water. Alright, so let's start by setting this problem up. That means we need to define the system. So defining the system for the heat exchanger is a little bit complex because we actually look at the system multiple ways. But we start off by looking at the heat exchanger as the system. So we're going to define this first of all. Our entire heat exchanger is the system. So that involves two substances. We have R134A and we have water. So classifying this system, the heat exchanger is an open system. R134A and water are both phase change substances. Next we're going to go to the sketch, and the sketch is kind of important for the heat exchanger because we have to make sure that we get all of the inlets and exits and everything correct. I'm going to jump to the new page so I can get a nice big sketch. Here is our heat exchanger. And remember, we're studying a shell tube heat exchanger. So we have on one side water. So I called water as substance A or whatever, it doesn't really matter. I called water, I gave it an inlet number of 1. So the water, if I kind of draw the water, it comes in, and let's say water is the one that goes through the tube. So water leaves at exit 2. So water is the one that's in the tube, and then we'll say R134A is the one that's in the shell, the outside part. So R134A, it comes in, and we'll call its inlet 3. and its exit 4. Alright, so here's our inlets and our exits, and let's go ahead and put some of the properties that we know at these values. So for the R134A, we know the property at the inlet pressure and temperature at the inlet, and then temperature at the exit. So we know P3, we know T3, and we know T4. For water, we know the inlet pressure, temperature, and the exit temperature. So very similar. We know P1, we know T1, and we know T2. Alright, so here's all of our properties. And then to start off, we're analyzing the entire heat exchanger as the system. So the system boundary is going to be around the entire heat exchanger. Next thing we have is our conditions. We have our general condition for Chapter 4, steady flow. Then we apply the heat exchanger conditions, like I've given it in the notes. So in the heat exchanger, potential energy effects, kinetic energy effects are negligible. Also, the work is negligible. And the heat transfer is negligible. Remember, the heat transfer for the heat exchanger, this capital Q dot, is the heat exchange between the inside of the system and the surroundings. So all of the heat is transferred within the system boundaries, so there's no heat transfer between the inside and the surroundings. That makes the heat transfer between the heat exchanger and the surroundings 0. So all of these are negligible. Also, one more thing that we are told in the problem statement, and this is something that we also typically assume, even if it's not stated for a heat exchanger problem, is that we neglect any pressure drops. What does that really mean? What that really means is that the pressure, P1, whatever pressure the water comes in at, it leaves at the same pressure. It doesn't have a pressure drop in the tube. So we can say that P2 is equal to P1. Also, same thing for the shell. Whatever pressure the refrigerant came in at, it leaves the shell at the same pressure. So P4 is equal to P3. Alright, now we can list out the properties. So for the properties, we know the very first thing we're given is the mass flow rate of the refrigerant. So the mass flow rate of the refrigerant, we're going to go ahead and specify that as m dot r for refrigerant. It is equal to 6 kilograms per minute. And then we want to convert that to kilograms per second. So to do that, we need to divide by 60. That's going to be 0.1 kilograms per second. That's the mass flow rate of the refrigerant. Next, we have the inlet pressure and temperature of the refrigerant, 1 megapascal and 70 C. So the inlet pressure, P3, is 1 megapascal. Inlet temperature, T3, 70 degrees Celsius. Next, we have the exit temperature, 35 degrees Celsius. The exit temperature of the refrigerant is number 4. So T4 is 35 degrees Celsius. So that takes care of the refrigerant. We also have some properties of the water at the inlet. The water has 300 kPa and 15 Celsius. So P1 is 350 kPa. T1 is 15 degrees Celsius. Sorry, that's not 350, it's actually 300. And then the exit temperature of the water is 25 degrees Celsius, so that would be T2. Alright, now everything is pretty much set up, ready to start solving. So in our solution, what we are actually looking for, got to be careful here, we want the mass flow rate of the cooling water. So we can call that m dot of the water, W. Also, we want the rate of heat transfer from the refrigerant to the water. So we're really looking at the rate of heat transfer for the refrigerant. So that's going to be something we call Q dot R. Alright, so now we know what we're looking for, and just like all of these problems, we are going to apply our two major equations, mass balance and energy balance, for each one of these problems. Let's look at the mass balance first. For the heat exchanger, we have multiple inlets and multiple exits, so we need to apply the MI-MO form of the mass balance, which says summation of the mass flow in is summation of the mass flow out. So we have two inlets. We have m.1 and m.3, two exits, m.2 and m.4. That's our mass balance. Can't really do much with it yet. Next we can write the energy balance. Energy balance, we also need to use the multiple inlet, multiple outlet form. Looks like Q dot minus W dot is equal to summation out. Next we have M dot H plus KE plus PE minus summation in M dot times H, KE, and PE. So if we rewrite this equation for the heat exchanger, we have Q dot minus W dot is equal to summation out. Well, let's go ahead and first we can cancel off any negligible terms. So we said that kinetic energy effect was negligible, potential effect was negligible, work was 0, and the heat transfer is 0 for the heat exchanger. So all that leaves us with is m dot times h at the out is equal to m dot times h at the in. So at the outlets and the inlets, at the inlets we have 1 and 3. The outlets we have 2 and 4. Alright, so the mass balance and the energy balance for the heat exchanger just by themselves aren't going to be super helpful, right? Because we don't really know m.1, m.3, m.2, or m.4. We only actually know the mass flow rate of one thing, and that's the mass flow rate of the refrigerant. So let's keep going, and we want to do an analysis of each one of the substances by itself. So the first thing we'll analyze is just the water flowing through its tube. So now what we're going to do, here let's make some equation numbers. This is equation 1, this is equation 2. Now we're going to look at water as the system. So analyzing water as the system, we can still write a mass balance for the water. The water itself is just one inlet and one exit device. It never mixes with the refrigerant. So the mass flow rate of the water says, or mass balance for the water says m dot 1 is equal to m dot 2. And what we can call that is the mass flow rate of the water. So m dot 1, m dot 2, that's the mass flow rate of the water. Then our energy balance says Q of the water minus W of the water is equal to delta H of the water plus delta KE of water plus delta PE of water. So for analyzing just water as the system, we can neglect potential energy and kinetic energy and work just like before. But for the water, there is heat transfer to the water, right, from the refrigerant. So we're not going to cancel out Q sub W. So we know that the heat transfer to the water is equal to delta H of the water, or H2 minus H1. So if we want the heat transfer to the water, we need properties H2 and H1. So let's label these equations. Here's number 3, here's number 4. Before we look up properties like H, let's go ahead and analyze the refrigerant as the system. So R134A as the system. We can do its mass balance. And just like the water, the refrigerant has one inlet, one exit. It never mixes with the water, so it is a single stream system by itself. So the mass balance says m dot 3 is equal to m dot 4, or that is the mass flow rate of the refrigerant. So the mass flow rate of the refrigerant is the one that we know. Then for the energy balance, we can write Q to the refrigerant minus W is equal to delta H, delta KE, and delta PE. Similar assumptions for the refrigerant as water. Kinetic energy, potential energy, and work are negligible. So we can write that the heat transfer to the refrigerant, this number should be negative because the refrigerant is what's hot, is equal to delta H of the refrigerant, H4 minus H3. So now we have our 6 equations, and we can start putting some of this information back together. Alright, so let's start off by looking at equation 1 and using some of the information that we found about the mass flow rates from 5 and 3. So looking at 3 and 5, putting that back into equation 1, says that the mass flow rate 1, that's the mass flow rate of water. Mass flow rate 3 is mass flow rate of the refrigerant. Mass flow rate 2 is mass flow rate of the water. Mass flow rate 4, mass flow rate of the refrigerant. So basically this equation helps us none because it's just a true statement. So this equation is just true. It doesn't help us solve for anything. Let's look at putting 3 and 5 back into equation 2. So from equation 2, we had mass flow rate 1, that's mass flow rate of the water, times H1, plus mass flow rate 3, So now m dot r times H3 is equal to mass flow rate 2, that's the water, times H2 plus mass flow rate 4 is for the refrigerant, times H4. So from this equation, we can actually find something useful. We can combine some like terms here and get an equation that looks like this. So now we have something that is a very useful equation. We have the mass flow rate of the water, that's what we're solving for. So let's solve for the mass flow rate of the water. It was equal to mass flow rate of the refrigerant times H4 minus H3 over H1 minus H2. So the mass flow rate of the refrigerant was given, and then we need to try to figure out H1 through H4 based on the properties of the substances. Alright, that'll give us the mass flow rate of the water. And then anything else that we want, we were also looking for the rate of heat transfer to the water or from the refrigerant. So we were looking for the rate of heat transfer to the water. No, we were looking for the rate of heat transfer, from the refrigerant. So we have the heat transfer from the refrigerant per unit mass is this. So from equation 6, we know that Q sub R is equal to H4 minus H3. And then since the refrigerant itself in the shell is a single stream system, we can find its heat transfer rate is equal to its mass flow rate times its heat transfer per unit mass. So this would be m dot r times H4 minus H3. And that turns out to be what is on this side of the equation, right? This is the heat transfer from the refrigerant. Alright, so we have our two equations now. Mass flow rate of the water is this, and it's based on properties that we need to look up. Heat transfer from the refrigerant is equal to this, and we need to look up those same properties, H4 and H3. So the rest of the problem is solved basically by looking at the properties. So let's just go through them in order, starting at the inlet 1. We have pressure 1 is 300, temperature 1 is 15 degrees Celsius, and we're talking about water here. So we can go to the tables and try to determine the phase of the water, since it's a phase changer. To determine the phase of water, we compare its temperature to the saturation temperature at the given pressure. So let me open up the tables here. Our pressure is 300 kPa, or 3 bar. So I'm going to go up into table A3 and look for the 3 bar. See what our saturation temperature is at 3 bar. At 3 bar, the saturation temperature is 133.6. Our temperature is 15, so it's much less than the saturation temperature. This means state 1 is subcooled. So state 1 is subcooled, and our pressure 300 kPa is too low to be in the subcooled tables. So we can get an approximation for the property value that we're interested in. We can say H1 is approximately equal to H sub F at T1. So looking up H sub F at T1, we'll need to go up into the temperature table. At 15 degrees Celsius, our H sub F is 62.99. That takes care of state 1. Now we can go to state 2 at the outlet number 2. At outlet number 2, we know that pressure was equal to the inlet pressure, 300, and our temperature has risen to 25 degrees Celsius. So again, we have to do the same steps, determine the phase, then we can get the property value H. Determining the phase, we compare T2 to the saturation temperature at P2. Since P2 and P1 are the same, they should have the same saturation temperature, 133.6. So T2, still less than the saturation temperature, still have a subcooled liquid water at the outlet. So same process, we can get H2 by using our incompressible liquid approximation, H sub F at T2. So T2 is 25 degrees Celsius, we read off H sub F, 104.89. That takes care of water. Now we can go to the refrigerant side in the shell. Looking at inlet number 3, we knew P3 was equal to 1 megapascal, and T3 is equal to 70 degrees Celsius. So just based on the fact that we know this is a condenser, we should expect that at the inlet the hot substance is superheated. But we still would need to check it. So let's check and make sure we get the phase of the refrigerant is correct. So for the refrigerant properties, I'm going to have to go into the book and I'm going to need to turn on the light. So the refrigerant 134A table starts with table A10. And we're looking for the saturation temperature at 70 degrees, or sorry, 1 megapascal. 1 megapascal is 10 bar. So here we see at 10 bar that the saturation temperature of refrigerant is 39 degrees. So we have, this is 39, it was actually 39.39 degrees Celsius. In this case, T3 is 70, it's higher than that saturation temperature, so indeed we do have a superheated refrigerant at the inlet to the condenser. So once we know it's superheated, we can get the property H from the correct superheated tables at P3 and T3. So going back into the tables, looking for pressure of 10 bar or 1 megapascal. So here's the subtable for 10 bar, 1 megapascal, and then our temperature is 70, so H is going to be 302.34. That takes care of state 3, and then last but not least we have outlet 4 for the refrigerant. Our P4 was equal to P3, still 1 megapascal, and our temperature now has decreased to 35 degrees Celsius. So first thing is check the phase. We know that for the hot substance, if it's a condenser, the phase should be at most a saturated liquid, but probably going to be a subcooled liquid. Let's go ahead and check it. I put T3 here, this is actually T4. So we're comparing T4 to the saturation temperature at P4 for refrigerant. P4 is the same as P3, so they should have the same saturation temperature, 39.39 degrees C. Our T4 is indeed less than the saturation temperature, so we definitely do get a subcooled liquid. So it definitely does condense the refrigerant from a superheated vapor down into a subcooled liquid. So once we have the subcooled liquid, there's no subcooled tables for refrigerant, so the only thing to do is use our incompressible approximation. H4 is approximately equal to HF at T4. So back into the refrigerant tables we go, looking for temperature T4 and the value of H sub F. So I'm in table A10. My temperature is 35 degrees. In the table, we only see that there is 34 and 36. So we're going to have to interpolate to get the property at 35, and then we're interpolating here between the HF values, 97.31 and 100.25. So this is going to be an interpolation. 34 was the table value, 35 is our value, 36 was the other table value. At 34 degrees, H sub F was 97.31. And at 36, H sub F was 100.25. So there is H4. Let's go ahead and calculate H4 real quick. Interpolation, 34, 35, 36, 97.31, and 100.25. So we end up with 98.78. Now we can actually answer our questions. So going back to our equations, solving for the mass flow rate of water. Alright, mass flow rate of water is equal to mass flow rate of the refrigerant, which is 0.1 kilograms per second, times H4 minus H3. Let me see what H3 was. H3 was 302.34. Then we divide that by H1 minus H2. So H1 was 62.99 minus H2 is 104.89. That means our mass flow rate of water is about 0.486 kilograms per second. So if we look at this, we're cooling down refrigerant from a superheated to a subcooled liquid from 70 degrees to 35 degrees Celsius. In order to do this, we need to provide water, cooling water at 15 degrees Celsius. And we need to provide almost 5 times the amount of cooling water as the refrigerant that we're actually cooling down, right? Because the mass flow rate of the refrigerant is 0.1, we are providing almost 5 times the amount of cooling water. Now let's see what is the heat transfer to the, from the refrigerant. That equation was mass flow rate of the refrigerant times its delta H. So Q dot R. We know that this Q dot R should be a negative number because the refrigerant is hot, so it's going to have a heat loss. And it's going to be equal to mass flow rate of the refrigerant, 0.1 times H4 minus H3. Put some parentheses here. We get negative 20.4. Our units here are going to be kilowatt. Right, we're multiplying mass flow rate in kilograms per second times kilojoule per kilogram. That gives us kilojoule per second or kilowatt. And then this is our answer. So one thing that I just want to show you here is based on our energy balance equation. Based on this equation that we ended up with, let me pull this equation down to the bottom. M dot of water times H1 minus H2 is equal to M dot of refrigerant times H4 minus H3. We already said that this was equal to Q dot R. And this one is equal to mass flow rate of water times negative delta H of the water. So delta H of the water from our equation, it's way up here, equation 4, delta H of the water is heat transfer per unit mass to the water. So the heat transfer rate to the water should be the mass flow rate of the water times heat transfer per unit mass to the water. So this term right here is actually the negative of this term. So this is negative Q dot to the water. So if we calculate the heat transfer to the water, we should get negative of whatever this answer we just got for Q dot R. Let's just check it and make sure. Let's calculate Q dot to the water. It's equal to mass flow rate of the water times H2 minus H1. So this is going to be equal to mass flow rate of the water times H2 62.99 minus H1 104.89. This should be equal to positive 20.356. Oh, sorry, I entered the equation incorrectly. Heat transfer to the water is H2 minus H1, so I need to switch this order. Alright, so we do in fact get the positive 20.356. or what we said was just basically 20.4. And then everything checks out correctly. The heat transfer rate to the water is positive because the water is receiving heat from the refrigerant. The heat transfer rate of the refrigerant is negative because it is having a heat loss to the water. And then we found that to do all of this condensing, we need to provide almost 5 times as much water to the heat exchanger as refrigerant.